Okay, so I've been interested in applications of AI to healthcare for many years, but since the beginning of the pandemic, I've been thinking and working on the question of how machine learning could help with drug discovery, and that's what I'm going to tell you about today. Initially, actually, we wanted to discover new antivirals, and this work is going on, but more recently, we've been working on the discovery of new antibiotics, which is like the next pandemic lurking. I'll tell you more about that. So, machine learning and deep learning are being explored in many areas of medical applications. It's interesting to consider their use when, of course, we have data that's could be sometimes a main bottleneck, but also where it makes sense, where traditional methods maybe are not satisfying, maybe because the data is very high dimensional, like images. This is probably the place where it's been most developed, or it's very high dimensional because it's things like genome, RNA expression levels, a lot of data about a patient history. And now with deep learning, we have methods that can process these kind of high dimensional data, of course, but also like sequential structure, textual data, missing data, censored data. And typically we would use these methods to make predictions, estimate probabilities for future events, predict properties of molecules, for example, in the case of drug discovery. But what I want to tell you about today is a bit different. It's about the use of machine learning to help not in a standard supervised prediction kind of framework, but in order to help do something different, which is help to search in the space of molecules, to generate new candidate molecules with desired properties, to plan experiments, biological experiments, drug discovery experiments, to discover causal structure of interest. So that's really what I want to talk about. I mean, the reason why we want to use machine learning is because we don't understand sufficiently the body, and especially the biochemistry of what's going on in cells, and of course how they interact with each other. There's a lot of knowledge, of course, in biology, but not enough to kind of reason directly from that knowledge and come up with therapies. I mean, in some cases, but in most cases, we're kind of going by trial and error, and we're collecting a lot of data along the way. That's where machine learning can make the most difference. Also, we can use the knowledge we have, whether it's from scientific experiments or from data, to build simulators, models that we can run quantitatively in order to help us plan decisions, like plan experiments, figure out what therapies we should try, what new drug we could consider, and so on. There's one of the most important breakthroughs in machine learning using deep learning, in particular graph neural nets and attention mechanisms, of the last few years is the work by DeepMind on the modeling of 3D protein structure with AlphaFold. So you're given the sequence of amino acids, and you're trying to find the 3D structure where each of the residues are going to be standing in space relative to the others. And this has been a hard problem that scientists, usually not using machine learning until recently, have tried to crack for decades. Right? And the progress has been very small. So you can see in the figure on the right, progress in the CASP contest to predict 3D structure, not making really significant advances until the first version of AlphaFold, and then the one from 2020 has really broken the record. Not only just broken the record, but gotten pretty close to the accuracy we can get experimentally with crystallography. So that's quite amazing, and it's not something we can you can use so directly right now. We need to extend this work, for example, to model how molecule complexes, so two molecules together, will place in space. But it's an amazing and super important first step towards a lot of problems in drug discovery and biology. Now, focusing a bit more on drug discovery, as I said, we could use fairly standard methods in machine learning, supervised learning, to predict properties of a drug candidate. We have examples for which we know this molecule has such and such toxicity, drug likeness, synthesizability, how much it binds to some target of interest, and so we could use machine learning there in a fairly standard way. But maybe more exciting is helping us understand what is going on, help us figure out new mechanisms in the cells to help guide the search for useful drugs, like which protein should we target, basically. So that's one problem. The protein from sequence, structure from sequence I mentioned, there's a lot of work that continues to improve on that. And can be extended, as I said, to the case of multiple molecules. Also, the AlphaFold proposes a deterministic solution that we know that proteins can take many conformations, and it's not sufficient to only generate one. So there's a lot to do to go beyond this. There is work more on the clinical side as well of drug discovery. Would like to make sure we can give the right drug to the right person. So personalized therapies, even potentially depending on the patient's genome or the patient's cells that may have been extracted and so on. That's very exciting for cancer in particular, because each person has a different cancer. And then there's the question of what to try next, whether it's a drug, whether it's personalized, whether it's an experiment to better understand what may be going on in cells of interest, whether it's a combination therapy. And the space of decisions we have to face in many cases is huge. And so this calls upon things that are more related to an area of machine learning called reinforcement learning, that I'll say a few words about, but I'll use concepts from reinforcement learning. I won't really give a course on reinforcement learning. Now, this kind of research becomes more relevant these days as the tools in biology to acquire data, to perform experiments on the large scale are moving very fast. So on the one hand, we have more and more automated tools, robotics that can do experiments, many at a time in parallel. And on the other hand, we have help from what's called synthetic biology, where we can reprogram cells like yeasts or bacteria, change their DNA so that they would produce proteins that we want. And then these proteins can be either the drug itself or could help as an enzyme to achieve some goal we're interested in. So the thing with synthetic biology is that we can program a huge number of cells with different sequences, right? So we can do an experiment where, say, 10 to the 4, 10 to the 8 different candidate sequences will be each sequence will be put in different clones that will synthesize that particular protein that we want, and then we can screen them in parallel. And there are various ways of doing that so that we can find out among that huge set which are the ones that are responding in ways we're interested in. And then the other thing that's happening is progress in machine learning. The number of people working on machine learning research and applications is growing exponentially in the last decade. And there's been progress that's very relevant, not only in deep learning, but things like representation learning, reinforcement learning that I mentioned, active learning, I'll talk a lot about, Bayesian optimization, I'll mention, notions of exploration that are related to reinforcement learning, notions of causality that I'll mention as well, meta learning, which has to do with how you can learn to learn from multiple learning iterations. And another area that I'm interested in, which is out of distribution generalization. In other words, how do we improve our machine learning system so that they can generalize to settings very different from those we use for training? And that's also relevant in biology because the data we may be using for training may not be quite what is going to happen when an actual drug is put in the blood of an actual person. And that's related to causality, as I'll mention later. Okay, so I mentioned the pandemic, of course, that pushed me into this research. And I'll talk about antimicrobial resistance. But one thing in particular that encouraged me to move forward here is that, unfortunately, there's not enough research and development in industry on many medical problems, like preparing for future pandemics, or like coming up with new antibiotics very quickly to face antimicrobial resistance. Sometimes, unfortunately, in many important cases, some innovation is really needed by society, can have huge impacts on health, on the economy, but it doesn't have enough commercial value for industry to do that research. And so we need, well, we need academics to be involved, but I think we also need to change the economic system. And if I have time, I'll say a few words about this at the end. How can we stimulate that kind of innovation? So let me say a little bit more about antimicrobial resistance. There's already 700,000 deaths per year due to the presence of variants, mostly bacteria, but also fungus and viruses, for which our current drugs don't work. And the reason, as we kind of all know now, is because these bugs mutate very quickly. And the more a drug has a chance to reproduce, the more mutations come up, and some of them will be kind of selected to be resistant to the drugs we currently have. And so there's a kind of race between humanities R&D department and evolution of these bugs that can kill us or make us very sick. And in particular, there's been studies predicting that this phenomenon of antimicrobial resistance is going to get worse and worse over coming years because we're using so many antibiotics, for example, that helps the bacteria to develop resistance. And the number of deaths is going to grow to 10 million per year if we don't do anything, when nothing is going on right now, by 2050. So that 10 million per death is probably substantially more than what we are getting with the pandemic. So you can see how devastating that can be to people and the economy. The economic forecast is this is going to cost globally $100 trillion US. And yet it's not profitable to search for new antimicrobial drugs. Now, the good news is, as I said, we can very cheaply try a lot of candidates. Like 100,000 may cost you $10,000 just to synthesize the candidates, and then because you need to do the experiments, but it's still very cheap. That means we can get a lot of data quickly, and that's important for kind of high-powered machine learning we could use here. Now, the challenge from a machine learning perspective is the search space is huge. We can't possibly screen all the possible small molecules or all the possible peptides. For example, here we're looking at peptides and the research I'm doing. There's just too many, like 10 to the 60, these kinds of numbers. So we need a strategy to explore that space. And that's where I'm going to focus. So yeah, the search is really exponentially difficult. Searching a needle in a haystack is a good analogy. Even if we have good computer models that allow us to predict whether a given molecule is going to work, I mean, it's never going to be perfect, but that's not the main issue. The main issue is we can't just call that program 10 to the 60 times if it has to find one in such a large number. Hopefully, many of them will work, so the fraction may be better, but still, this is food for thought, and we should develop methods for searching in such high-dimensional spaces. Right, so the first thing we want to do is the supervised learning I talked about. We have data, say we have some set of therapies, say drugs X, and we have experimental results, maybe clinical results, that tells us how useful that drugs seem to be. Usually we're going to have like lots of data of what we don't exactly want, like maybe from single cell experiments, in vitro experiments, and a little bit of data of things we really want, like actual humans or mice taking those drugs. But we can just do supervised learning, right, and then screen those molecules. But as I said, there are too many of them. And even if we get very smart about how we do this screening, maybe we parallelize computation, we have a very fast, cheap model, and so on. The most we can hope by just screening is a linear gain. So the question is whether we can get an exponential gain, right? So how can we do that? Well, if we accept that we're not going to be able to try every molecule within some family, say, then the right thing to do is to search in that space, right? In other words, to try things, but not randomly. And the space of molecules is mostly a discrete space. So how do we search in a discrete space? And I'm going to tell you a little bit about how we might do that. But one thing we did in our work, and other people have done similar things, is in the case of drug-like molecules, we can make the search a bit easier by doing it not in the space of atoms, like this atom goes here, this atom goes here. There's lots of choices, but we know that there are frequently occurring rigid blocks of atoms, molecule fragments that are like a vocabulary to build molecules that seems to be recurring. And then searching how to add those pieces together is actually easier. In the case of sequences like proteins, peptides that are short proteins, we can just add one amino acid at a time. But even there might be interesting to think about kind of a more hierarchical structure behind how we search. Now, in order to train a reinforcement learning agent, like think about you've probably heard about DeepMind's Atari game playing agents or Go playing agents. You need to give these reinforcement learning agents a feedback for things they do. And here, things they do would be constructing candidate molecules. Now, the problem is, one problem is the kind of feedback we'd like to have, ideally, is, try this molecule on a person. Well, we can't do that for a lot of reasons. It's too expensive or slow. So we're going to have to use proxies, and people do that already in the pharmacological world. Like, as I said, mice is going to be easier than humans, and working on single cells is going to be easier. And sometimes working even just like a preparation where we see whether the molecule binds to the target protein. So there's a hierarchy of cheaper oracle functions that are not what we want, the expensive one as what we want, but we can't afford to ask that many questions to the big oracle. We can also have a proxy for the reward, which is a trained machine learning system. So we can take the data we have and we can use our supervised learning to train an approximation of what would happen if I did an experiment in vitro, and then that's useful because I don't need to run the in vitro experiment. I can just query the machine learning predictor and use that as a reward. Okay, so that's a progress. We have to deal with the fact that there's errors and uncertainty and so on. I'll come back to these kinds of things. We can be smart about how we design these softwares as well. It could be a big difference. Using these machine learning proxies can, if it's designed well, can lead to huge speed up. So there's an experiment we run where we got a 250,000 speed up compared to an existing scoring function for drug synthesis. How synthesizable is the molecule using a trained neural net, a special kind of neural net that works on graphs that I'll mention. And we got a huge speed up using that. So the graph neural nets, they take the data represented as a graph with quantities attached to the nodes and potentially to the edges. And what they do is, you can think of it like we have the same little neural net sitting on each node, and it's going to iteratively compute its hidden state, its internal representation, by looking at the representations of the neighbors and with the edges that the graph has, and then all the nodes are doing that in parallel. And so together they're computing something that eventually depends on the whole graph, and you can read off predictions for the whole system from these graph neural nets. That's kind of how they work. And they've been amazingly successful, and that's kind of the technology we use anytime the input is a graph, like a molecule. Right, sorry. Yeah, here. Now let's go back to the question of how we could go from a linear speed up to an exponential speed up. Well, there's a very simple idea from computing and mathematics, and that is optimization. So if there's a function that has some structure, in other words, it's not like random values for each configuration of the input of that function, like the function on the right that we see here. On the Z is the value of the function on the vertical axis, and XY would be the inputs. Right. So if we're looking for a high value or a low value of that function here, we're minimizing. We don't need to try all the configurations, actually. We can use optimization to make small steps towards something better. And of course, chemists do that all the time. They have a reasonable candidate, and then they'll try small changes and see if that improves. And then they keep the things that improve and continue doing this. This is local optimization. It's a little bit more complicated in our case because the space is discrete, but you can still do it. And you can use a generalization of optimization called Monte Carlo Markov chains that I'll tell you about, because maybe you don't want to get stuck in a local minimum, right? So there may be many regions that have these, locally looks like the best solution, but there's a better solution in a different region of space. And so we'd like to have methods that can discover these good solutions, which we also call modes, and I'll tell more about that. Okay. So let's try to put together, synthesize a little bit some of the things I've said. So now we have like three things in the picture, as you see in the figure. On the right-hand side, you have the actual, say, biological experiment. Maybe it's in vitro. And when we perform a real biological experiment, we obtain data, let's say XY pairs, say X is a molecule and Y is a scalar that tells us how useful that molecule seems to be. So that constitutes a training set, and we can train a machine learning predictor. So that's the guy in the middle, and we learn a function f that can now be applied on new x's that we have done no experiment on. Okay, so that's the guy in the middle. The guy on the left, that's the one with a little imagination icon. That's the one which imagines new candidates. That's the one that does the search. Okay, so it can query the function f, which we're going to call a reward function, on new x's, but it queries the proxy reward function. It doesn't query the biological experiment because that's too expensive. Right? So we can do that much in an inner loop in the computer. That loop on the left here is all in the computer. So what do we want from that guy on the left, which the imagination machine? It's going to generate new candidates. So it's going to be a kind of generative model. You can also think as a policy, a stochastic policy, if you think in reinforcement learning. In other words, it's taking decisions and it's going to get rewards. If it guesses something that has a high value of f, then it's going to get a high reward. And its job is to think of maybe new places where f may be high. Of course, it can also do a local search. I mean, it can propose things in the neighborhood of things that it has already found to be good. But that's the easy part. We don't need like sophisticated machine learning for that. But we are going to be using sophisticated machine learning for the left-hand side, rather than just simple local optimization or Monte Carlo Markov chains, MCMC. Right. So, so that's the high-level structure. And as I mentioned, we also have to take that in the perspective that these oracles that tell us how good is a drug come at different levels of precision and costs. Right? So we can have cheap machine learning in terms of computation, expensive machine learning in terms of computation, or memory, whatever. Then we may have computer simulations, like very cheap computer simulations, like docking, that tries to figure out whether a small molecule is going to fit into a target protein, for example. Or we can have more expensive simulations. It's still in the computer, molecular dynamics, where we try to simulate the physics of these atoms and these molecules moving around. And then we can go to actual experiments. So in vitro cell lines, in vivo mice, and clinical trials. So there's this funnel, and usually the way it works in drug discovery is we just take the things that have worked best from the previous stage and try them on the next stage. And then if we don't converge to anything before we reach the final stage, we go back and try more things. So that's a very simple algorithm, but I'm pretty sure we can do better using machine learning. For example, we could imagine learning from all of the stages that follow, even though it's small amounts of data, downstream, it's still data, right? So we shouldn't be just using the next stage. The data from the next stage, like just the say in vitro cell level experiments. If we have even small amounts of richer, more precise data, we should use it. This is called multi-fidelity oracles in the jargon in machine learning. And what I envision with these kinds of tools is an ability to both explore how the cell works and explore, what would be a good treatment, even potentially personalized. So you can imagine we take, let's think about cancer. So we can take cancer cells from a patient and then do experiments where we try some drugs or we try some perturbation of those cells. We can knock some genes. We can throw some drugs, potentially multiple drugs at the cell, and then kind of see what happens. Look at what's called a phenotype. We can look at the activity in the cell, which proteins are expressed, and so on. And we can use that data to feed back on the machine learning system that proposes experiments, and hopefully quickly converge in a few iterations to something that does what we want. Maybe if it's a cancer cell, kill the cell, produce apoptosis, right? So this is the kind of machine learning tool we want to bring together. Now, there's one aspect of this whole endeavor that I didn't mention yet. While we're doing those experiments, we want to be able to generate a diverse set of candidates. Why? Well, if we only search around the things we know, we might make maybe small refinements, and typically, existing drugs have already been optimized, so there may not be much to optimize. We need to really be able to generalize far from the data, and when we propose candidates, we want to propose candidates that are sufficiently different from each other. Why? Well, if we're going to do an experiment, I said we can do experiments sometimes with hundreds, thousands, or even hundreds of thousands or millions of candidates in parallel. So if I'm going to do 1,000 experiments, I don't want the 1,000 experiments to be all more or less the same, right? I'd like to be able to explore in many different regions in the space of potential candidates, right? So we want the potential candidates that I'm going to propose with my experimental planning system to be diverse. So that's why we need exploration, diversity. And now the point about uncertainty is we're doing an exploration. So think about a child that is discovering a new territory, or a scientist doing experiments. It's important to think about how much information we will gain through the experiment. And that has to do with the learner's uncertainty. Like, in places where I already know what the outcome of the experiment would be, there is no point in doing the experiment. I want to do an experiment for which I don't know the answer yet. And how much uncertainty I have about the experiment should be something that matters. And I'll come back to that. Okay, so there's a literature in machine learning and even outside machine learning on what's called black box optimization that we can write on for many of these tasks. So the idea of black box optimization is you're given a function f, but you don't know f. You're able to call it. That's why we also call this an oracle. So you can think of the oracle as the biological experiment. I don't know how it works, but I can do the experiment. So I can provide an input, and I'm going to measure some things, and let's call that output. So in black box optimization in particular, we're interested in one particular output, which is a quantity we'd like to maximize or minimize. And so there's been a number of algorithms that have been proposed for deciding what next input to try. And in particular, one thing I'll come back to is called Bayesian optimization. Now, in our case, we want a variation on that where it's not really optimization. We want it something more like exploration. So we want this notion of diversity as well. And this could be applied to discover new drugs, but it's really a general purpose tool for scientists for discovering new things, new materials, answering questions about things we don't understand in nature, and so on. And in my own research in another area of my research on reasoning and causality with deep learning, these same tools could be used to search the space of explanations for things we observe, but that's a different discussion. All right. Now, in Bayesian optimization, but also in what's called active learning, an area that's been around since the 90s, we can do this kind of black box optimization, but the setup is a bit different from what we want. The setup is that somebody gives us a list of candidates for which we don't know the answer, we don't know the outcome of the experiment. And we're not going to try all of them, that would be too expensive, but we're going to pick some of them by computing something for each of them, like for which one do we have most uncertainty about the correct answer, F. So in other words, the F that we're looking for is something we don't know, and we need to keep track of how much error we think we're going to make in different places, so that we can maybe peak in those places where the uncertainty is greatest. The problem with that setup is the list that I really care about is 10 to the 60 things. I can't even compute 10 to the 60 things, even if each of these things was very cheap. So we need to add this generator, this policy that's going to propose things, right? So that's where we're going to depart from classical active learning. Right. So again, to summarize, the machine learning system we want to build is going to propose a batch of candidates. Typically, we're not going to do one experiment at a time. The batch might be small, like 10, or it could be very big, like 1 million. And then there is some black box thing, which could be biology, could be some more expensive computation, could be a proxy that's been trained on data from the biology, like I said earlier. But now let's focus on the generator. How are we going to train this, right? So it has access to the data points that have been collected, but its job is to propose new candidates. So here's a slightly more involved picture of what we're trying to achieve. All right, so on the right, again, it's the biological experiment, the oracle. Let's call it the real world. And in the middle, we have what I'm now going to call the world model. So it could be our supervised learning predictor based on the data we have already collected from the real world. We're trying to predict some things of interest. But now we're going to add an element to this, which is epistemic uncertainty. In other words, the model knows about its own failures. It knows that there are things it doesn't know. And there are different degrees to that, right? So I'll come back to how we can do that. And then on the left, the thing that I want to focus on is this reasoning exploratory agent that's going to imagine experiments. Now, there's the question of how we're going to train that guy. Okay, so it's trained to produce things that are interesting. So we need a kind of measure of interestingness, and we need that measure to be computed quickly. So it's not going to be based directly off of doing the actual experiment in the real world. The way we're going to train that generator, that policy, is by trying it in our mind, in the computer, if you want. And we're going to use the world model and its epistemic uncertainty to come up with a reward function, a quantity, a scalar that tells us, oh, this would have been a good experiment if we had done it, right? We could have learned a lot from it in the real world. For example, this is a molecule that might be very good. We're not sure, but there's a chance that it could be very good. There's a lot of uncertainty on the sense of it could be very good. If there's a lot of uncertainty that it could be very bad, but there's no chance that it could be very good, then we're not interested, of course. So we need to cook up some measure, some reward function that's going to be used to train the policy on the left, so that it's going to train itself to propose useful experiments. All right. So there's going to be this loop, right? We're going to use the trained policy to generate candidate experiments once the policy is trained. And that's going to be sent to the biologists, the real world. They're going to do experiments. We get data back. We accumulate all that data in a data set. We use that to update the world model, including its knowledge of its own uncertainty. And then we retrain or fine-tune the generator, the policy, so that with the modified world model, it learns to generate good questions. And the change could be quite significant, even if only a little bit of data, because maybe there was an experiment for which we didn't know the answer, so our uncertainty was high. But of course, after we do the experiment, now the uncertainty for that experiment is going to be low. So we don't want to ask that same question again. So the uncertainty function is going to change in some places quite a bit, of course. So really, it is important to update our imagination machine, our experiment planning machine on the left. Okay. I thought maybe if that works for you, I could do a small pause here for some questions, because I've been maybe saying a lot of abstract things, and what comes next is even more abstract. So I want to make sure people track. I'm going to stop sharing right now. And if that's okay with the organizers, I'm going to take a couple of questions.
Yeah, that's fine. Thank you. So I suggest that any question be put on the chat if there are any. From my viewpoint, it's not yet clear yet to me how we can stimulate and augment the efficiency of the generation of what you call the epistemic uncertainty. What would be the methods to facilitate creation of these new questions that we may have, which, as you explained, should be sufficiently distant from one another?
Right. So there's actually, a small but fairly long literature in machine learning about epistemic uncertainty. But the simplest thing you can think of is using Bayesian methods. So if you're Bayesian about the predictor, what it really means is you don't believe that there's just one function that is the answer. You have a distribution over functions. So in places where those functions in your distribution disappear, like if there is a lot of, if there is a molecule for which your Bayesian model says there are many possible answers, I don't know which one is correct, then you have high uncertainty, right? So I'll come back to simple methods people are using to estimate Bayesian. Not necessarily Bayesian, but epistemic uncertainty. But yeah, that's
okay, fine.
In a way, and you can also use the errors you made in the past to know how much uncertainty you should have in something. I see some. I
see that there is a similar question. In the term of diversity raised by Anna, for instance.
Oh yeah, diversity is something that has been less explored.
Yeah.
And like we're trying fairly simple things, like you can measure distances between the candidates. Or any kind of similarity. So in the case of molecules, we have some similarity functions like Tanimoto distance or similarity. And so when you generate your batch, you can filter it so that you make sure you only keep sort of representative examples. You can generate more than you need and then keep sort of clusters, like you can do kind of clustering, for example. So that's a very simple way you could do that. But yeah, it's not obvious how to do that right. And another thing we're looking at is training the generator so that it generates not just each candidate independently, but given the candidates that it has already generated, what other candidates could it generate that would be rewarding? And they, you would pay a price, of course, if you generate something that looks like anything you've done before. So there are different kinds of methods to do that, but yeah, there's a lot of new things to explore as well.
Okay, then Romain is asking if the energy function reflects how useful a new protein can be.
Yes. So I use the word energy here, not in the physical sense, although it could be sometimes also the physical energy. Low energy of binding indicates that something interesting is happening. But generally, I use the word in the machine learning sense, which has to do with probability. So this is something we want. Low energy is something we want. P equals e to the minus energy normalized. And I can also use the word reward, which is just e to the minus energy. So something, whatever word you use for this, there's something you'd like to be high or low, and you'd like to generate those high values, but you'd like them to be different.
And Jan is asking if we include some prior knowledge about molecules and components, especially regarding side effects and so on.
Yeah, of course. You want to use as much prior knowledge as you can without destroying, what data could bring. So it's not always completely obvious how to do that. But yeah, a lot of the art in machine learning is how to put together things we know from the science here, like chemistry or biology, in the design of the machine learning systems. So in the example I gave where we search in the space of small drugs, small molecule drugs, one piece of knowledge we use, actually pretty big piece is we are searching in the space of these fragments. So instead of adding atoms to some existing scaffold, we add these fragments. And in addition, we use chemistry to know which fragments could be put where, right? It's not any atom cannot go anywhere in a partial molecule. So that's a lot of chemistry knowledge.
Okay, then the question about the world model raised by Aiden. How is it created a priori in your paradigm?
Well, so the world model is what you've, it may incorporate your prior knowledge, but mostly it's been trained on the data. So it's the result of the kind of supervised learning. We have data. From that, we build a model. That model could be Bayesian or something that captures uncertainty, and that's the world model. Now, I call it the world model because I want to, we can generalize this idea to general AI, but in the case of drugs, it's a model of the effect of drugs.
And the question about the smoothness of the space, which is a large one, as you say, 10 to the power 60.
Yeah, it's not smooth, but there is structure. So smoothness is a very simple form of structure, and it makes it easy to do these like a local search. But the nice thing is machine learning can exploit all kinds of structure. If we use these graph neural nets, they don't need to learn the smooth functions, but it needs to have regularity. Like if it's completely unpredictable what the outcome is for a new configuration, then machine learning is not going to help. If there is structure and it's discoverable from the data, which sometimes you need enough data, then it's going to help.
Okay, and then perhaps one last question. Okay, we'll take Eve as well, but I think we should go back later. So Flora is asking if you try generating new proteins molecules by first training a machine learning model to predict the output, and then freeze the model's weight and go to a gradient ascent to generate new inputs. Yeah,
that's right. So people have tried that. Well, so first of all, the problem is the input is discrete, so it's not that easy, but you can still use tricks and do that, but it only does a local search. So what I'm proposing is something a bit smarter, where in addition to that model that predicts Y given the molecule, we train a second model that's like a generative model, and it guesses good molecules, and it's getting a reward when it guesses good ones. So that's the idea of what I've been talking about, the summary of everything I've talked about since the beginning.
Okay, and then there was a comment rather than a question by Eve, who was confirming the interest of trying to find the solutions to the resistance to antibiotics, which of course is a major public health issue. Okay.
Yeah. And diversity, as he writes, is crucial there. Absolutely. All right, so I'm going to share my screen again.
Okay.
Okay. So I think At least the people who asked the questions seem to got the picture. There is interesting question, and we have some evidence that the answer may be positive, which is whether, as the system, that we're building, that both models the data and learns to ask questions, gets trained with more and more data, is it becoming easier for it to search more efficiently? So the question is, what does it mean to search efficiently? So if you think you have a very high dimensional space, you can ask the question of, how many calls to the oracle do I need to find a molecule that has a certain level of what we want? So that's what the figure on the right shows. On the x-axis, on the log scale, you see 10 to the 2, 3, 4, 5, 6, 7. This is a number of calls to the oracle, the number of experiments that I might do. On the y-axis is, here it's docking energy, it's something, actually would be minus energy, or something like this. High is good, right? So, and what we're plotting are the best we found up to now. So, I've tried, say, 1 million things. What's the best score, the best reward I got? So these curves can only go up, right? So now you can do these experiments, we can do these simulations, and we can see how fast we progress. In other words, on this log scale, and how much better do we get with respect to that score? And we see that there's diminishing returns, that initially you seem to progress very fast, but eventually it takes more and more examples to make progress. In fact, typically it needs exponential, it gets exponentially bad. And so that corresponds to a straight line. All right, so it's kind of sad, but yeah, it's searching in an exponentially large space is exponentially hard by default. So it's not surprising we get these straight lines. Now, what may happen though is some models, some approaches, some algorithms may have a straight line with a different slope. So the slope tells us how fast, even though it's exponential, it might be exponential with a better exponent, right? So here we have the two, the green with M1 slope and the blue or orange with M2. All right, so that's interesting because the model M2 is exponentially better, like faster to search than the model M1, and with the slope M1. And then there's another thing that seems to happen, and that's interesting, which is as the learner sees more and more data, the slope can change. It can get better. And that makes sense from a machine learning perspective, right? Because as initially it sees data and it doesn't see any structure in it. So it's kind of random searching. And then eventually it sees some structure. So now it's going to make its search easier and the slope is going to get better. So the curve should go slightly up as we continue seeing more data. So that's kind of plots that are interesting to make. All right. Let's go back to the question of epistemic uncertainty. So first of all, we need to distinguish two kinds of uncertainties. The epistemic uncertainty, as it's called, and aleatoric uncertainty. So aleatoric uncertainty is the nature, is what's unpredictable in nature. Even if you had full knowledge of the causal structure and you had infinite computation, you would still make mistakes because there is noise, right? So that's aleatoric uncertainty. There's nothing you can do to predict better than what's called, the Bayes optimal predictor. All right, now everything else that the best possible predictor could do is due to a lack of the predictor. You don't have enough data, you don't have the right model, you're making errors that could have been avoided. That's epistemic uncertainty. Epistemic means knowledge. So you lack of knowledge, potentially lack of computation, means you're doing these errors. And when we're thinking about planning experiments, we need to make a distinction between these two things, because we don't care about doing an experiment that's noisy. I mean, for which the uncertainty is intrinsic. We care about doing an experiment where we could learn. In other words, after the experiment, we'll be better off than before. In other words, the model has reduced its uncertainty, because of course, after I've seen data for an experiment, well, I know the outcome of the experiment, and maybe if I can generalize, I can predict correctly in other parts of the space. So it's really epistemic uncertainty we're looking for. Unfortunately, they're not necessarily easy to distinguish. If you look at just the error that's being made, it's a combination of both. All right, so there are many ways to estimate epistemic uncertainty, and there's still a lot of research to try to improve. As I mentioned earlier, many of the methods are derived from kind of Bayesian perspective. So in Bayesian optimization, we're getting not just a function as the result of training, we're getting a distribution of the functions, and we're gonna organize things so that we can compute the variance at a point X across the functions that we believe in of the predictions of those functions. So that's kind of Bayesian variance point-wise. So we can compute that. It's a function we can compute for every X. Of course, we can also make a point-wise prediction that's just like the average function. So at each point, we now have like a mean and a variance across the functions. And that's the blue sausage that you're seeing. The thick blue line is the mean function. And then around each point, we've added plus or minus sigma. All right, so that's what comes out of Bayesian learning. The red points here are like the places where we have data. So you can see the uncertainty here, that variance, which is a proxy for epistemic uncertainty, is 0. We know the answer if there was no noise in the data, let's say. And the dash thing is the true unknown function. And hopefully, if the Bayesian thing is doing its work, it's kind of sitting inside this kind of confidence interval in function space, right? So, so now, given that information, how could we decide where to look? Well, we want to look in a place where we could not just gain information, which would just be like places where the variance is high, but gain information where it matters to us. So it matters to us in places where, like if we want to maximize, where the, say, the mean plus the standard deviation is large. And so that's called the UCB for upper confidence bound heuristic. It's a heuristic. And there are many other heuristics. You can use the Bayesian information to come up with what's called acquisition functions that are kind of heuristic that tells us, this is a good place to look at given the mean and given the uncertainty. There is also maybe simpler methods in the case of neural nets, which is to train a bunch of neural nets, say K neural nets, and they are initialized differently. So turns out they will come up with different answers. And if you just look at the variance across their answers at a particular point, it's actually a pretty good predictor of epistemic uncertainty. It's very coarse, but it's very easy to instrument. You don't need any new code, basically. And that's used a lot. Another, a bit more sophisticated, but also pretty easy, is MC dropout, Monte Carlo dropout, where you use a technique that was introduced about 15 years ago, maybe more, maybe less, like 12 years ago, where it was first introduced as a way to introduce noise in neural nets so that they would be regularized and generalized better. And it's a very special kind of noise where you turn off some units. You basically set them to 0. It's like, we have the normal neural net and we randomly are going to drop out some of the nodes. And so we have like a sub-neural net that's left out, and we use it to make our prediction. And we can draw different binary masks here that shut off these neurons. And each time we're going to get a different answer. We can train this whole thing so that they're kind of, it's robust to the noise, right? So all of them, for any noise pattern, binary mask pattern you choose, is kind of trained to do a good job. But depending on this binary pattern you choose, it's going to give a different answer. So they're kind of all consistent with the data, but different. And again, that gives you a variance which you can use for epistemic uncertainty. There's another approach which we introduced last year, where you train a second network to predict the error of the main network. And that has some advantages in terms of not being so dependent on the parametric assumptions that the Bayesian approach is making. For example, if I think about my ensemble, like let's say I have an ensemble of 3 networks, but they have the same architecture and they're all too small and whatever, it's not the right architecture. So the variance may be small, but they're all wrong together. And I won't know by looking at the variance. But still, I have a lot of epistemic uncertainty because I could reduce that error if I was training a larger network. Yeah, let me skip the details of that. Okay, let's go back to diversity. So the basic tool we're going to use first for diversity is very simple. It's sort of the magic of IID sampling, right? Let's say okay, so what we want is how to explain this. What we want is our generative model to produce a distribution that has that is as spread out as possible, that has high entropy, that covers all the potential interesting places. If our distribution is focused in one place, like it's unimodal, it's one Gaussian, it's like, well, there's really like one type of solution and then little variation. That's not good for us. So we want a generator that's going to be designed so that it likes to cover all the possible good places. We say, it covers all the modes of the reward function. So the reward function is this function that we want to be high. So we want to generate in all the places where the reward is high, right? So one way to put it is we get a distribution of our generated things where the probability is proportional to the reward. And if we can do that, then in order of n computation, we can cover the modes. Basically, it's very surprising how IID sampling is powerful. I mean, that's to get diversity, because the other option, and we can combine both things. The other option is to look at a batch of candidates, like I said earlier, and then try to kind of measure distances between them. But that's n squared, right? So if we can have an order of n method, that's good. And in fact, what we use is a combination of both. So we're going to train a generator that's produced diverse solutions by construction when you just sample IID from it. And then we're going to sample a batch, and then we're going to filter it to try to keep just the clusters or the things that are different from each other. All right, so now I'm going to tell you a little bit about what I'm most excited about in my research in the last few months, which is an approach to build this kind of generator, this kind of stochastic policy that produces diverse candidates. We call them G-flow nets, for generative flow networks. So what they do as a job is kind of similar to what you could use Monte-Carlo Markov chains for. So given the reward function, which you can think of as e to the minus energy function, we want to obtain samples with probability proportional to that reward function. All right, so we're looking for PT equal to reward up to a multiplicative constant. And of course, that multiplicative constant is troublesome because in order to sample, we might need to compute it implicitly, and that's intractable. So the standard way of solving this problem is to use Monte Carlo Markov chain methods, but there's an issue with it that I'll try to explain. So MCMC methods, basically, intuitively, if you've never heard of them, what they do is they stochastically and intuitively modify a good candidate. So they're like optimization methods. They tend to go towards better solutions, but they can also randomly go up in the energy. And with some probability, in fact, they will jump from one local minimum to another one. The problem is that if these local minima are far from each other, then the probability of kind of finding a path between them is going to become exponentially small. And so that's where machine learning comes in. Also, if we already have some candidates, like we've seen some data, we know about, we've explored some region, we'd like to be able to kind of guess other places that are far. So in this figure here, I have these 3 regions that I have visited, and I found like good rewards in those regions. So there are 3 modes of the reward function. Now, if I just do small local moves like we do with MCMC, there's almost no chance that I'm going to end up in some other mode that's kind of far from these I have already visited. So it seems hopeless, right? And you can play all kinds of tricks to improve this with MCMC that are tailored to the task. If you know something about that structure, you can exploit it. But in general, it's hard. So what we can do is we can train a generative neural net. So think about, all the work that, for example, we've done in my group with GANs. So GANs are generative neural nets. They're trained on things like images, say images of faces, and they will generate images of new faces that don't exist. How do they do that? They might even be images of people that, not only they don't exist, they are far from anyone that they've been trained on. Well, because they find structure in the distribution. So for example, here, turns out these 3 modes, these 3 like high regions, they're sitting on the intersections of this grid. So a good machine learning system, having seen these 3 modes, might guess, hey, maybe there is another mode at this other intersection I haven't visited yet, right? So this is what machine learning can do. It can, instead of being blind about all the things that have been tried yet in the Markov chain, for example, we can use everything that we have tried as data to give clues about where there might be other things, potentially very far, that are also interesting. Because there is structure, there is a regularity, like this very simple grid-like regularity, but in general, it's more complicated, right? With MCMC methods, the problem is that in order to go from one mode to another mode that we haven't visited yet, we have to kind of guess the right direction to take. And then we have to traverse a kind of desert of low probability where the chances of continuing on that path that's smaller and smaller probability is exponentially small. The probability of a path is the product of the probabilities of all the steps. It's much more likely to go back to the good things that it has seen before. And so if the modes are far from each other in high dimension, and in addition, if they occupy small volume, it's very hard for MCMC methods to work well. So the small volume thing is that, of course, there's another way to find those modes, which is to throw darts. Right? If I can just do random things and then locally improve, that's a well-known method for optimization, global optimization. That works if the regions that are interesting have these like large basins of attraction. And then I can just get into one of these basins, go down and find a minimum. Unfortunately, it's not always like it could be sharp, those changes, as probably the case for molecules. All right, so these G-flow nets, they try to replace MCMC by this policy that's going to sequentially construct a solution. So up to now, I've discussed the molecule as if it was like one thing, but really it's a sequence of decisions. I add this fragment and then that fragment at this place and then that fragment at this other place, or I add this amino acid and then that one and then that one. So it's a sequence of decisions, right? So we can think of the probability distribution for generating such a sequence as going through all these steps, and we have a policy that given the steps we've already taken, chooses the next step, and in particular, given a state corresponding to the choices we've made up to now. And maybe there are many paths to construct the state. So if I've constructed a partial molecule, it's not yet like a stable molecule, but it has a bunch of atoms. I could have achieved that from many ways through different ordering of adding things. So we have a method that takes that particular structure into account. And let me use this picture to illustrate what's going on. So we think of generating a solution here as the sequence of transitions. And what you see here is an example of a directed acyclic graph corresponding to all the possible paths in the space of, say, constructing a molecule. And so the squares here correspond to like a final molecule. And the triangle on the left is the initial like empty molecule. And at each step, we may add a fragment. And now the policy we're gonna be choosing is based on looking at relative probability of taking one edge coming out of one of those states, which is like a partially constructed molecule, relative to the other edges, the other changes I could do to that molecule. And mathematically, the way we're solving this problem is we're thinking of a flow. We're thinking of like water that comes from the initial state and flows everywhere in the graph and eventually lands in those final molecules. And the probability of taking one action, which corresponds to a transition here, is going to be chosen proportional to the amount of water, the amount of flow in that edge. And we can train a neural net that is going to calculate how much flow should be everywhere, given that we know how much flow should be in the terminal states. So, and we know that because we have a reward function that says, well, for this molecule, this is how much you would get. So we can query that function and we can sample trajectories corresponding to constructing a molecule. And at the end, we know how good that trajectory is because we can call our oracle, our proxy, our world model, our reward function. And then we're going to adjust the flow function that tells us for each edge, you know, how likely it is compared to other ones. And then we do it again and again. And it turns out we can prove things about this. I've said this already. Oops, I'm moving too fast. Here. So we can prove things. I'm not going to go through the math of this, but what we can prove is basically that there are many actually loss functions that we can define that, you know, given a trajectory and given the reward that we get at the end, if we minimize that loss function along those trajectories and we sample a lot of trajectories and we minimize in average across all these trajectories, then we converge, if we have enough capacity in the neural net, to a policy that is the one we want. In other words, that sample configurations in proportion to the reward function. And that's pretty extraordinary. In addition, it tells us the partition function of that reward function. It tells us the intractable, it estimates the intractable sum over all the possible molecules, say, of the reward in the flow of the initial state. Because if you go back to this figure, you can see that if we estimate the flow in every node and edges, we can read off the total flow here, even though we've not visited all the nodes. It's gonna like guess based on things it has seen how much flow should be everywhere. And so how much flow should be at the beginning is the total of all the flows, all the molecules rewards. All right, so it's a bit different from regular RL because regular RL is trying to do something more like optimization, is trying to find a sequence of actions that gives you the maximum reward. Whereas here, we're trying to estimate a distribution over actions that samples the things we want in proportion to the reward. So it's kind of a different goal. And it turns out that you can compute all kinds of useful things, as I mentioned, partition functions, but also marginalize probabilities over like subsets of variables. You can compute things like entropy, which would be useful for epistemic uncertainty. The difference with regular MCMC is that we're learning how to search rather than having a fixed recipe, and that learning can take advantage of all the samples we've already acquired. Also, in its basic form, the JFlowNet is much faster because once it's trained, it's one pass through the neural net gives us a sample. We don't need to have a long chain, and because it's discovering those modes more easily, because it bypasses this mode mixing challenge, if machine learning does its job, you tend to get a more diverse set of samples. And yeah, I'm going to skip these other things. So we have in Europe's paper, which I should show the authors of that. Wait, I don't know why things are very slow. Do I have it? Yeah, so that's the Europe's paper. Emmanuel, Moksh, Maxime, Doina, and me. And in that paper, we have already some experiments exploring the ideas that I mentioned, but not all of them. And we find kind of what I promised. So we find that compared to established methods for searching in the space of molecules, so either based on traditional RL, PPO being one of these methods, one of the most commonly used ones, and a method used, MCMC methods used for sampling molecules, we find that if we draw these curves of like how many things do I need to query in order to get something good, so that's the middle figure, we can see that it discovers good solutions much faster. And in addition, and the figure on the right also, so Mars is the MCMC method that I mentioned, that's in orange, and PPO is in green, so that's the RL methods, and the blue is ours. And if you look at the like top 10 or something like this, it really finds better solutions, but in addition, it finds more diverse solutions. So that's the figure here. Again, on the x-axis is the number of queries that we've made to the reward function. On the y-axis is the number of modes. So we use Tanimoto distance to kind of cluster, separate the molecules in different groups, and we want to see how many groups that are at least some distance away from each other this can discover. And we find that at some point it kind of gets it and discovers many more modes than the competing methods. All right, there were many other things I wanted to talk about, but I want to leave time for questions. The topics I wanted to talk about were about applying some of these G-flow nets in the context of not just discovering drugs, but discovering pathways in cells, causal pathways, which of course could be useful for drug discovery, but also for understanding how cells work. And where the experiments here are not, try this drug necessarily. It could be try this drug, but it could be knock out a gene, and then the measures might not be, whether or not the drug works or the extent to which it works, but more high-dimensional things like what's happening with the expression of the cell. And I won't have time to talk too much about this, but there's a whole field of causal machine learning that's kind of making slow progress, but a lot of excitement there in the last years. There was a NeurIPS workshop that I co-organized, and more recently, so traditionally it was more like graphical model types of approaches, and more recently deep learning methods, and my group has been contributing to that in the last 3 years. But I think we're just at the beginning of an era of using deep learning in the context of causal discovery to discover the graph structure, the underlying causal structure, and plan these experiments using machine learning, using the kinds of techniques that I mentioned. All right, I'm gonna stop to leave some more time for questions, and thanks.
Well, thanks a lot for this talk again. It's impressive to see how the mathematical concepts can be expressed in terms of the world. I think this is one of the lessons that I take from your talk. So again, please ask questions in the chat. In the meantime, I was surprised by your conjecture where you say that slope should increase with more data and therefore super exponential. Because I would have argued that the problem may become more and more complex as far as you come close.
No, you get
to
more
solution.
data. No, you each time the x-axis is how much data you're collecting.
Yeah. Okay.
So you acquire more knowledge. You start to understand how the world works.
Yeah, but then if you look, for instance, at the adequacy of molecules to microbial resistance, isn't it possible that the problem of finding the optimal solutions become more and more complex?
No,
I mean,
no, you don't. No? Okay, so let me try to repeat so I think you have a different picture. It's not what I'm doing.
Okay.
What the picture you have in mind is try the molecules you think are good first, and then enlarge the circle. That's not what's going on here. We're saying every peptide of 50 amino acids is up for grabs, or every small molecule of some size is up for grabs. Now that's a big space, and we search in that space. And of course, you're allowed questions. Now the questions may be naive at the beginning, and eventually they become smarter, and that's why you get more efficient in the rate at which you can acquire information. Eventually it will saturate. So in simple problems I showed, toy problems, eventually eventually there's nothing to learn anymore and it saturates. But we are in like an exponential rise where the more you learn, so think about science, right? The more we know, the smarter we can be about the experiments we can do, and we can do experiments that gather more information. Initially we're naive, so we kind of like the baby playing their hands around, and we try random things. It's very inefficient. But eventually the baby learns to do those things, and now it can search in a more pointed way, right?
Okay, fine. Any question on the chat?
I will share the slides, sure, no problem.
Yeah. Please. In one of your last slides, I was surprised by the sharp change in performance. The one where you were comparing the various...
for the diversity?
Yeah, because it had been flat until 10 to the power 5 or something like that, and then but suddenly, how do you explain
that's not unusual. That's not unusual in machine learning. So a common thing we see when we train a neural net is plateaus. So sometimes at the beginning where things are really bad, it learns very slowly, and then it's like it's found the trick that explains the data, and then it learns very fast. And sometimes you have multiple plateaus like this. I mean, it doesn't happen in every experiment. The typical experiment is it just goes down and then saturates. But these plateaus happen, when you have complicated optimization problems.
Okay. Okay, so I guess this was quite clear, and there's no additional questions. So
I think the second half was a bit more abstract, and that's why I wanted to have questions for the first half.
But I think the slides will be useful for all of us to, and perhaps come back to you. So one question by Stanislas. Do you entertain memory storage problem?
No, because we're not trying to store 10 to the 60 things. There's no such thing. There's a neural net that has a small size. It has never seen 10 to the 60 things. It doesn't store 10 to the 60 things. It has seen only the data that's been, it's been trained on, which are like the results of experiments, and it generates new candidates in a space of size 10 to the 60, right? Which is just molecules, right? So each molecule is not that big, and maybe we generate 10 to the 6 things, or 10 to the 7, or 10 to the 8, but not 10 to the 60.